Welcome to this module on problem-solving and decision-making. These two skills are the very heartbeat of effective project management. Think of a project as a journey from a starting point to a final destination. No journey is ever entirely smooth. You will inevitably encounter unexpected detours, roadblocks, and challenges along the way. These are the problems of your project. Your ability to navigate these issues with confidence and clarity will determine whether your project reaches its destination successfully. It is not about avoiding problems, as they are a natural part of any complex endeavor. Instead, it is about being prepared to face them head-on with the right tools. This module is designed to give you that essential toolkit. We will move beyond simple guesswork and gut feelings. Instead, we will explore structured, proven methods that bring discipline and logic to your work. A great project manager is not just a planner or a scheduler, they are a master problem solver and a decisive leader. They can look at a complex situation, break it down into manageable parts, and identify the best path forward. This requires more than just experience. It requires a deep understanding of specific techniques and frameworks that can be applied consistently across different types of projects and industries. Throughout your career, you will find that projects are dynamic and constantly changing. The initial plan you create is merely a starting point. The real work begins when that plan meets reality. A client might change their requirements, a key resource might become unavailable, an unforeseen technical issue could emerge. In these moments, your value as a project manager truly shines. Being able to analyze a problem calmly, evaluate your options systematically, and make a well-reasoned decision is what separates a good project manager from a great one. These are the skills that build trust with your team and your stakeholders. In the following sections, we will delve into the specific tools and mental models that will empower you. We will cover everything from defining a problem with precision to analyzing its root causes and selecting the optimal solution. You will learn how to handle uncertainty, make choices when the future is unclear, and ensure that your decisions lead to real, lasting positive change for your project. By the end of this module, you will not see problems as threats to your project's success. You will see them as opportunities to demonstrate your expertise and guide your team towards a successful outcome. In a project environment, a problem can be formally defined as a perceived gap between the existing state and a desired state, or a deviation from a norm or standard. Problems are not exceptions, they are an expected part of the work. An effective project manager is not someone who avoids problems, but someone who approaches them with a structured, analytical framework. A reactive approach leads to firefighting, where symptoms are addressed instead of root causes. A formal problem-solving framework ensures a disciplined and thorough response. A widely used model is the Define, Measure, Analyze, Improve, Control (DMAIC) cycle, originating from Six Sigma quality management. Define, clearly and objectively define the problem. What is the specific issue? What is its impact on the project's objectives? This involves creating a formal problem statement. Measure, quantify the problem. This involves collecting data to understand the current state, the baseline, and the magnitude of the issue. Analyze, perform a root cause analysis to identify the underlying cause of the problem. This stage seeks to find the vital few causes that contribute to the majority of the effect. Improve, brainstorm, evaluate, and implement a solution to address the root cause. This involves developing and testing potential solutions before full-scale implementation. Control, monitor the implemented solution to ensure it has solved the problem and has not created any unintended negative consequences. This involves creating a control plan to sustain the gains. Decision-making is the cognitive process of selecting a course of action from among several alternative options. To make effective decisions in a project, we often rely on models. A model is a simplified, abstract representation of a real-world system or process. Because real-world project systems, with their complex interplay of tasks, resources, stakeholders, and risks, are often too complex to analyze directly, we create models to help us understand their behavior and predict the outcomes of our decisions. Models can be physical, for example, an architectural model of a building; schematic, for example, a flowchart of a process; or mathematical. The goal of a model is not to be perfectly accurate, but to be a useful abstraction for analysis and decision-making. Many critical project decisions must be made under conditions of uncertainty. In decision theory, it's important to distinguish between risk and uncertainty. Risk exists when the future outcomes of a decision are not known, but the probability of each outcome occurring is known. Uncertainty exists when the future outcomes are not known, and the probabilities of them occurring are also not known. Sensitivity analysis. This technique helps determine which variables have the most potential impact on a project's outcome. For example, by changing the estimated values for various risks in a financial model, a project manager can see which risks have the biggest potential impact on the project's profitability. This helps focus risk management efforts on the variables that matter most. A common visual tool for this is a tornado diagram, which graphically displays the sensitivity of the result to changes in each variable. Scenario planning. This is a creative and strategic technique where the team develops several plausible future scenarios. For example, a best case, worst case, and most likely scenario for market adoption of a new product. The team then develops a strategy that is robust across all scenarios or creates contingency plans for each. This moves beyond single-point estimates to embrace a range of possible futures. Monte Carlo simulation. This is a powerful computer-based technique used to model the impact of uncertainty on a project. Instead of using single-point estimates for task durations or costs, we provide a range, for example, using a 3-point estimate. The simulation then runs the project hundreds or thousands of times, each time randomly picking a value from the range for each variable. The result is not a single outcome, but a probability distribution of all possible outcomes. This can answer questions like, what is the probability of finishing the project within budget? Or, what is the likelihood of meeting the October 25th deadline? Linear programming. This is a mathematical technique used to achieve the best outcome, such as maximum profit or lowest cost, in a mathematical model whose requirements are represented by linear relationships. In a project context, it could be used to optimize resource allocation across multiple projects to maximize the overall value to the organization, given a set of resource constraints. A project manager's toolkit should include several proven tools for structured problem-solving, particularly for root cause analysis, which is a systematic method of problem-solving aimed at identifying the fundamental causes of problems or incidents. The 5 Whys, a simple but powerful iterative interrogative technique used to explore the cause and effect relationships underlying a particular problem. When a problem occurs, you ask, why, 5 or more times, with each answer forming the basis for the next question. Fishbone diagram, also known as a cause and effect diagram, this tool helps a team brainstorm and categorize the potential causes of a problem. The problem itself is the head of the fish, and the major categories of causes, for example, people, process, technology, environment, form the bones. While a fishbone diagram is excellent for linear cause and effect relationships, some problems are systemic and involve feedback loops. Cause-effect cause analysis is a more advanced technique that helps visualize these circular relationships. It encourages systems thinking, a holistic approach to analysis that focuses on the way that a system's constituent parts interrelate and how systems work over time and within the context of larger systems. It is invaluable for understanding and solving recurring, persistent problems that seem to defy simple solutions. A decision tree is a graphical tool used to analyze decisions under conditions of uncertainty. It maps out the possible outcomes of a series of interrelated choices, allowing a project manager to select the path with the highest expected value. A decision tree has 2 types of nodes. Decision nodes, squares, represent a choice that the project manager must make. Chance nodes, circles, represent an uncertain event with multiple possible outcomes, each with a specific probability. The analysis is done by calculating the expected monetary value, EMV, for each branch of the tree. EMV is a statistical concept that calculates the average outcome when the future includes scenarios that may or may not happen. It is calculated by multiplying the value of each possible outcome, the path value, by its probability of occurrence and summing the results. The analysis starts from the right side of the tree and works backward. folding back the tree to the initial decision point. Example: a project manager in Hyderabad must decide whether to use a proven existing technology or a new unproven technology for a project. The new technology, if it works, 70% probability, will result in a profit of Rs 50 lakhs. If it fails, 30% probability, it will result in a loss of Rs 20 lakhs. EMV of new technology, 0.70 Rs 50 plus 0.30 Rs 20 equals sign Rs 35, Rs 6 equals sign Rs 29 lakhs. The old technology is guaranteed to work and will result in a profit of Rs 30 lakhs. EMV of old technology, 1.0 Rs 30 equals sign Rs 30 lakhs. Based on this analysis, the rational decision is to choose the old technology, as its EMV is higher. Not every decision requires a complex mathematical model. For day-to-day problem prioritization and decision-making, several simple but effective frameworks exist. SWOT analysis, a strategic planning tool used to identify and analyze the strengths, weaknesses, opportunities, and threats related to a project or a decision. Strengths and weaknesses are internal to the project, while opportunities and threats are external. The Eisenhower Matrix, a powerful time and task management tool. It helps prioritize problems by categorizing them into 4 quadrants based on 2 dimensions: urgent and important, do immediately; important but not urgent, schedule to do later; urgent but not important, delegate; neither urgent nor important, eliminate. A decision support system, DSS, is an information system designed to help managers make decisions by providing access to and analysis of data. In the past, this might have been a complex spreadsheet model. In today's context, a DSS is more likely to be a sophisticated real-time project management dashboard powered by data analytics and even artificial intelligence. These modern systems can provide descriptive analytics, what happened; diagnostic analytics, why did it happen; predictive analytics, for example, forecasting the likelihood of a delay based on current performance trends; and prescriptive analytics, for example, recommending the best course of action to mitigate a risk. Chaos theory is a branch of mathematics that studies the behavior of dynamic systems, systems that change or evolve over time, that are highly sensitive to initial conditions. This phenomenon is popularly known as the butterfly effect, where a small change in one state of a deterministic nonlinear system can result in large differences in a later state. For a project manager, the implication is a lesson in humility. For truly complex, innovative projects, it is impossible to predict every outcome perfectly. The goal of planning and decision-making in such an environment is not to create a perfect, rigid plan, but to build an adaptive and resilient project system that can sense changes in its environment and respond to them effectively. It favors agile, iterative approaches over rigid, long-term predictive plans. A decision is not complete when it is made. It is complete only when it is successfully implemented and its results are monitored. The follow-up phase is critical and often neglected. It involves communicating the decision, clearly communicating the decision and its rationale to all affected stakeholders. Implementing the decision, assigning responsibility and resources to execute the chosen course of action. Monitoring the results, tracking the outcome of the decision to ensure that it has solved the intended problem and has not created any new, unintended negative consequences. This is the control step of the DMAIC cycle, which ensures that the gains from the decision are sustained. Scenario: an IT services company in Chennai is facing a recurring problem. A major client has repeatedly complained that the software builds delivered at the end of each month are of low quality and full of bugs, leading to customer dissatisfaction and unpaid invoices. The project manager, Priya, has tried addressing the symptoms, adding more testers, but the problem persists. The initial analysis, Fishbone. Priya gathers the team and uses a fishbone diagram. They identify several causes. Developers are rushed, testers don't have enough time, and requirements are unclear. This is helpful, but doesn't explain why these conditions exist. The deeper analysis, cause-effect-cause. Priya decides to dig deeper using a cause-effect-cause analysis. She starts with the core problem, low quality of monthly builds. This causes the client to be unhappy. The unhappy client causes a delay in invoice payments. The delayed payments cause the finance department to put pressure on the project manager. The pressure from finance causes Priya to pressure the development team to deliver features faster to get something billable out the door. This pressure causes the developers to cut corners on unit testing. Cutting corners on testing is a direct cause of the low quality of monthly builds. The aha moment. The team has discovered a vicious cycle. The pressure to solve the financial problem, delayed payments, was directly causing the technical problem, low quality. The effect had become the cause. The solution. Armed with this insight, Priya stops pressuring the developers. Instead, she goes to the finance department and the client with the diagram. She negotiates a change in the payment terms. Instead of billing for a large, low-quality build at the end of the month, the team will deliver smaller, high-quality, fully tested feature sets every 2 weeks and bill for those. The client agrees, as they prefer receiving working software more frequently. The finance department agrees, as their cash flow becomes more predictable. The pressure on the development team is lifted, quality improves, and the vicious cycle is broken. Lesson. This case demonstrates that for complex, recurring problems, a simple linear analysis is often insufficient. A systems thinking approach using cause-effect cause analysis can uncover the hidden feedback loops that perpetuate the problem, leading to a much more effective and sustainable solution.